Okay, hello everyone. Welcome to the second session of Robotics Lunch. Today we have our own Shushman, who is a PhD student working with Janet Book and Michael Cohenderfer. He's going to be talking about large-scale multi-agent routing.
He also works with Dorsa.
Oh, okay. Yeah, also with Dorsa.
Yeah, as I've made this joke before, but if you haven't heard it, I'm that Indian cousin that shows up everywhere to every wedding. Okay, so hi everyone. Yeah, thanks for coming to the Robo Lunch talk. Just before I jump in, this was mostly the talk that I gave in my quals. So if some of you seen that before, feel free to tune out. I won't mind. But feel free to also jump in the middle if you have any questions or interrupt. It's not like super recorded. I think it's about 35-40 minutes. Might go a bit longer because I've introduced some extra material from that previous talk. But we'll see. So yeah, so today I'll be telling you about some of the work that I've done with my collaborators, Kirill and Marco from ASL and one of my advisors, Michael, on controlling a large fleet of agents and routing them over transit networks across like broad urban areas. And there are a number of funding sources that supported us. Ford funded me, the Toyota Research Institute funded Marco and Kirill, and this work is part of a larger NSF grant. It's actually pretty interesting, started recently on trying to solve this large-scale multi-agent routing for delivery over transit networks. And I'll talk a bit more about that in a second. Okay, so also can everyone hear and see me properly? If not, just let me know at any point. All right. Oops. So, you know, I don't need to tell any of you that one of the prominent trends in urban life over the last few years has been this explosion of e-commerce demands, especially one-click and instant delivery. And the overall effect of this, other than making us get our various products more quickly, has been to increase congestion due to delivery trucks on the street, especially nowadays, although I guess there aren't as many people driving nowadays, but thereby impacting travel times for both public and private vehicles. Also, this talk was made pre-COVID land, so if there are any assumptions that no longer hold, you know, too bad. However, I think we'd all agree that in general, there are definitely ways and reasons to think about improving the current package distribution pipeline, especially in cities where they get quite congested. So delivery drones, with their flexibility, agility, and aerial reach, have been a quite promising alternative. We've seen Wing and UPS start to do things. But of course, as you may know, they suffer from their limited range and payload capacity. On the other hand, the existing ground-based transit networks do have much better coverage and throughput. So if we could somehow coordinate these aerial and ground networks and combine their strengths, then hopefully we would achieve not only commercial benefits for the operators, but also a bunch of positive societal outcomes like reduced street congestion and faster delivery of essential goods. So in our paper, we have the following setup. In some city scale area, there are some warehouses or depots, and we need to control a large number of delivery drones to carry packages from depots to the requested locations. The drones have the ability to use public transit vehicles, say a bus network, as temporary modes of transportation to save energy and increase flight range. We need to decide what deliveries to make, in what order, and whether or when to use these modes of transit. So as a disclaimer, here we'll be working at an algorithmic abstract level, the highest level of the decision-making stack. Of course, the actual deployment of such technology in the streets is a highly interdisciplinary task, and the other collaborators on the NSF grant I mentioned earlier are working on some of the other aspects. And in case you think I'm being too futuristic, this is just, I just pulled this a while ago. This is a screenshot of the NSF grant and you can see the name is quite optimistic, Synergetic Drone Delivery Network in a Metropolis. But of course, the embellishment of research grant titles aside, I think what this is saying is that there's really a concerted effort to kind of get these technologies deployed. I'll say one thing, if you notice the title of the talk said multi-agent routing over transit networks, while the rest of the talk and this title here is drone delivery. I'll be using them quite interchangeably. I just used multi-agent routing rather than specifically drone delivery because the level of abstraction at which we're working could apply to other multi-agent settings where, say, an aerial agents are being routed over ground agents. Another example that I often bring up is if you're exploring the surface of a planet or some unknown terrain, and you need both ground vehicles, say a Mars team, for example, right? And you need both ground vehicles to take ground samples and copters or drones to take aerial pictures of surfaces, of like vertical surfaces, then a lot of these methodologies and ideas and motivation would apply there as well for more energy efficient and robust team missions. So this is a fairly challenging problem, as you may already have guessed. Let's just take a look at some of the pressing computational challenges. We need to plan routes over large time-dependent transit networks. Individual drones have a flight constraint of their maximum flight range. So we also have inter-agent constraints, which I'll talk more about later. We need to not only find routes for these agents, but also solve this allocation problem of which drones deliver what packages and from what depot. And ideally, we'd want not just arbitrarily feasible solutions, of which there could be many, many, but we want to optimize some cumulative objective over all drones, right? Because there are human costs involved, there are resource costs involved here. And in this work, we'll be considering the make span, which is, I think, is the L infinity norm. It's the worst delivery time for any individual package. But there are there's the sum of costs, and there could be other objective functions as well, which our framework could apply to. So in principle, we could have tried to frame the entire thing as this gigantic mixed integer linear program and throw our best Groby solvers at it. However, and I'm happy to talk about this more if it's of interest, for the real world problems, the scales that we care about, the business scales that we care about, which are hundreds of drones and thousands of packages, and the way that these constraints are set up, in general, even state-of-the-art methods will be a non-starter because they're far too general and don't exploit the problem structure at all. Now, I'll say this right at the start, the classic researcher's hedge. We don't actually compare against mixed integer LPs primarily for that reason. Maybe it's possible for some extremely motivated, state-of-the-art engineering team to try and frame this just as a MILP instead of going with our approach. So that's something that you'll have to take at face value for now. But this is our best intuition based on the methods that we did investigate. So our approach is as follows. We develop a framework that decomposes this problem and solves it in a two-layer approach. For the upper layer, we design a delivery sequence allocation algorithm that obtains an approximately optimal solution in polynomial runtime. And for the lower layer, we execute this allocation by extending multi-agent pathfinding techniques to find bounded suboptimal plans over large transit network graphs that respect all of the individual drone and the inter-drone constraints. And in addition to the theoretical properties, we present a few experimental results with two real-world public transit networks in North San Francisco and the Washington DC Metropolitan Area, with up to 200 drones, 5,000 packages, and bus networks of nearly 8,000 stops. On the commodity hardware on which we run these simulations, our framework can compute high-quality solutions where, say, the real-world make span of a set of deliveries is less than 2 hours, which means a set of deliveries, the worst, can be executed by a drone using these real-world networks and timetables in under 2 hours for the larger scenarios. And drones can extend their range, their nominal flight range, by up to 360% using transit. Of course, these are just snapshots of some of the results, and I'll go into the results in a bit more detail later, but this is kind of the summary of what's coming up. So just to give you a very, as I said, this is an abstract level, so this is all in an algorithm land. But to give you an illustration of what that lets us do, here's a simple visualization, I haven't played it yet, in North San Francisco with, I think, about 80 drones. And those gray boxes are randomly generated delivery locations. A few of them, as you can see, are over the water because it's a little challenging to filter them by what's on the land. But if you want a delivery on the sea, if you need your coffee while you're on a cruise, then you can do that. And I'm going to play this now, and maybe I'll pause it at times. So of course, this is just simulating. I'm just going to pause it here. This is simulating the drones being released from the depots and heading off to the delivery to which they have been assigned. And if they're red, it means that they're currently using transit. And I'll keep playing this. And you can kind of see some drones are going to nearby deliveries, coming back. Some are red, which means they're currently on a bus. And my favorite part of this video is the one at the end. If you look at the little agent at the top right. So I'm actually going to pause here. What's happened is the agent had to make its delivery. Its flight range has already been exceeded. So it doesn't have any more battery or very little battery power left. So it's now going to have to wait until the bus gets close enough to the depot to which it has to return, because drones only carry one thing at a time. And then right at the end there, you see, and kind of did what you expect, right? For certain outlier drones where they're really going assigned to like these far off locations and there's no easy way back, they're going to ride the bus until the very end and then fly off. So the point of this simulation is just to show that the algorithm is kind of doing what we expect. And even when the data is not purely synthetic, but is generated with real locations and real world public transit networks, as we'll see. Since we're only showing one delivery per drone here, there are only 80, but in practice, we can do a lot more, and I'll talk about that. Okay, so here's a brief map about what I'll be speaking of. Most of these are fairly brief, so it won't take as long as it might appear it will. Okay, so let me quickly go over what we can use from previous related work. I'm only highlighting a couple of representative papers in each case. As with any good idea, we're not the first to consider it. There's been some work on thinking about pairing aerial and ground vehicles. The nicely named flying sidekick traveling salesman optimization problem. It sounds gimmicky, but this is actually a pretty well cited paper in the OR community. They consider pairing one drone with one delivery truck. However, they don't consider much larger and more time-constrained public transit networks as we do. And there's no notion of allocations or conflicts because it's just a single controllable agent. Yours truly did some work last year, which I presented at my previous Robo Lunch talk last year, on planning and executing routes for a single drone with multiple modes of transit. It was in a sense a precursor to this paper. But once again, it was a single agent view that had no notion of allocation involved. Mobility on demand and vehicle routing are closely related, well-studied problems, and Marco Pavone's lab, they specialize in this line of work. Some recent work from their group studies the combination of ride-sharing services and public transit for individual passengers, but their agent models are typically very simplified, so they don't really consider inter-agent constraints. And in general, these approaches are not suitable for autonomous pathfinding, which is what we have to do. On the UAV side, there's been extensive surveys of civil applications that look at possible cooperation strategies, but they all generally present mixed integer LP methods that scale poorly or heuristics that don't have any formal guarantees, which again, can be in this large scale business scenario where there are real costs involved. It can be nice to have good quality solutions. And finally, from a more robotics AI perspective, the centralized multi-agent pathfinding community has done a lot of work on this fairly computationally hard problem and its variants. There's some work on joint task assignment and pathfinding, though their allocation model is quite simplified compared to ours, and there's no notion of transit networks. And there's some work on UAV traffic management in a city, but it's also unsuitable for similar reasons. And then as I go into our approach, we'll talk about how some of these, I wouldn't even call them limitations because that wasn't the scope of that work. They're focusing on different aspects of the problem. So before I jump in, the point is not to say that, oh, we are presenting a method X that beats all these other previous methods on some metric. It's more of, we're framing this hard real world problem in a way that previous approaches haven't really considered all of the nuances that we are. And now we're trying to propose methods that solve them, period, in a reasonable way based on some real world metrics that hopefully motivate the approach and make it worthwhile. And that's what we look at in the results. So there won't be a baselining against some previous method, in case you were wondering. So let's get an overview of the formulation and methodology in our framework. You probably guessed what's coming up. I'm using the North San Francisco scenario as the backdrop of our formulation. There's a set of product depots whose locations are given to us. We receive a batch of K package deliveries over a business day. and there's a team of M delivery drones. And you notice I cluster them at the corner because the drones are not necessarily associated with a particular depot. That's something that we'll have to decide as part of our framework, as part of the allocation problem. And of course, we have a ground transit network that we have access to. So in this framework, our overall objective is to route drones to deliver the packages with minimum make span, that is minimizing the maximum delivery time for any package, while respecting the maximum flight range constraints. So that's our overall objective, regardless of any notion of transit networks. The ability to use transit makes more problems feasible by extending the effective range. But it also makes computing solutions much more challenging than if drones could only directly fly to the locations and back. And if you think about it a little bit, you can kind of see why that's significantly increasing the problem scope and size. A few algorithmic assumptions that we make for simplicity here. Each drone carries one package at a time, which is fairly reasonable given payload constraints. We're not so focused on the dynamics level of the drone. So here we have a very simple dynamics model where the drone flies at a constant average speed. The previous work that I talked about in the single agent setting takes a bit of a deeper dive into thinking of the dynamics level aspect of the drone. And we can talk at the end about ways of combining this work and that work. Depots can contain as many drones as needed. So if it's useful to, we can release all M drones from the same depot, although usually, of course, that won't be useful. And finally, the transit network, we assume we have access to it, and it follows a given timetable without any delays or disruptions, which is a standard assumption in a lot of transit planning work. Toward the end, I'll talk about lifting some of these assumptions and what we can accommodate already and ideas for accommodating some of the other lifting of these assumptions. So, as I said before, we have two layers in our approach. The upper layer is for task or delivery sequence allocation. It takes as input the depots and package locations and some estimate of drone travel time between these locations. And it solves a threefold allocation that assigns each package to a dispatch depot and to a delivery drone, and each drone to a sequence of deliveries in order. The lower layer is for routing these drones or for doing multi-agent pathfinding. It takes the drones and their start and goal locations that were obtained from the task allocation as input and the transit network, and generates detailed routes in both space and time that respects all of the system constraints and the transit connection timings based on the average speed model of the drone. So that's the overview of our approach. And when I discuss the approach, I'll stay not at sort of a high level. I won't go to the lowest level given time, but happy to discuss offline. Now, let me provide an outline of the task allocation layer. So remember, we have as given the depot and the package locations and the M drones. What we want is a set of M paths, one for each drone, of minimum make span, which is an objective over the collection of paths, that start and end at the depot, at a depot, such that their union visits all the package locations exactly once. And if you think about it, that's kind of what we want, right? We want the drones to go around, visit the package locations once, and then come back to a depot once they've delivered the package. So this problem is a special version of the M traveling salesman problem, and we call this the M minimal visiting paths problem. And this variant is known to be NP hard, even when M is just one. And the best polynomial time approximation factor isn't all that great either. So we are working with a fairly challenging problem, even just at this layer. So our approach is defined into a bunch, can be broken down rather into a bunch of high-level steps. The first high-level step is to define the so-called allocation graph, a directed graph of depots and packages. This is fairly intuitive. The edge weights for this graph are some travel time estimate for the drone between those locations. For now, assume that they're given, but of course, the quality of that estimate is very important to our overall framework, and I'll come back to that. We can also model any arbitrary dispatch constraints through this formulation. That is, if a certain depot, for whatever reason, cannot deliver to a location, then that edge won't exist. The next step is to find the minimal connecting tours. What this means is that each package has basically to solve an assignment problem such that each package has exactly one dispatch depot from which that package will be sent out with the drone, and one return depot. And all the inflow and outflow constraints of the depots are respected. This can be done through, and we do this through an integer linear program. And the reason I put integer in parentheses will become clear subsequently, but it's really a linear program. And this step implicitly generates a collection of tours on this allocation graph. The next step is to merge these tours that were obtained from step 2. We do this by iteratively merging the depots that we considered into clusters of depots based on a metric of which 2 depots are closest to each other. And this uses standard hierarchical clustering techniques from the network community, where we have these all of the depots initially. We consider the 2 that are closest together based on some minimum edge weight metric. We then combine them into one cluster, and then that becomes like this meta depot. And then we keep doing this. And the result of this is one merged tour, PT, that visits all the packages and agglomerates the depots into like one cluster. And then finally, we split or partition this tour into M paths, one for each drone. Essentially what happens is we have this one tour, and we go along the tour and we split it into M chunks of roughly equal weight. And then each path PI, which is where I is 1 to M, encodes the sequence of package deliveries, one for each drone. So let's take a step back. We started with the set of depots and packages, and through this algorithm, this routine and these 4 steps, we now have a set of M delivery sequences, one for each drone, that starts at a depot, visits a certain subset of the packages, and going back to the depot in between to get the next package and so on, and then ends in a depot. And we do some post-processing to make sure all of that happens, such that the union visits all of the package locations exactly once. And that's precisely what we want, right? This gives us a delivery sequence for each of the drones. Now, the reason we've split it up into all of these steps is so that we can get the properties that I'm going to talk about, and the paper, especially the journal version, which is in prep, goes into a lot more detail. But at a high level, this is giving us what we want, a delivery sequence for each of the drones. So this allocation algorithm, we call it merge split tours, not a very inventive name. We show that in some detail that it obtains an approximately optimal make span solution, where those 2 slack factors are much smaller than the optimal if the number of packages is much larger than the number of drones. So M is the number of drones and VP is the set of package vertices. And this is usually the case for most real world scenarios. The number of packages in a day is much larger. And then we also prove that it has a polynomial runtime in the size of the allocation graph, which is the input to it. The key step there is showing that the parentheses integer program that I told you, the minimal connecting tours, that's the bottleneck, by the way, of these 4 steps. And that integer program can actually be solved as a linear program with fractional relaxation, such that the solution to the relaxed LP is actually integer optimal. And that comes from reducing the known minimum cost circulation problem, which is a modified flow, max flow problem, to our step 1, the minimal connecting tours problem. And specifically, the constraint matrix has this totally unimodular form. And for such problems, the LP relaxation is known to be integer optimal, which is pretty cool, because then you can make an IP and LP. And then all of the other steps are polynomial anyway. So that was the bottleneck. And this makes the entire routine polynomial. And we'll see runtime results that back that up. Okay, so that was, again, a high-level outline of what's happening at the task allocation layer. Just going to take a bit of a sip here. It's funny, this is exactly the point where I took a big water sip in my qual stock of deja vu. Okay, so now I'll discuss at a high level the second part of this, the second layer of this framework, which takes as an input the result of the task allocation, which is the delivery sequence for each drone. So you don't have to remember anything about the allocation, just remember its output, which is the delivery sequence for each drone. So the goal of this multi-agent pathfinding layer is to compute paths for the drones, potentially using transit. It might not make sense for some drones to use transit, that actually execute these deliveries. Now, since drones can only carry 1 package at a time, At this layer, we'll focus only on the first depot delivery or package delivery return, the first such task for each drone simultaneously. And we'll assume that subsequent deliveries, we can execute them in a receding horizon fashion when one of the drones finishes. I'll talk a bit more about that later. But this helps us frame it as a multi-agent pathfinding problem, which is a known problem. And what we want here is we want a set of MPaths, one for each drone, that has low make span, which is our true objective, if you remember. So we want the worst travel time of any of the MPaths to be as low as possible. And we want all of these paths to satisfy the constraints that we have on the flight range of the drones and their drone interactions on the transit, which I'll get into shortly. So that's what we want from this layer. Once again, we're going to abstract the problem to the essential model, which is what we call the multi-agent pathfinding transit graph. I'm going to use MAPF in short hereafter for multi-agent pathfinding. In this graph model, and this is a standard formulation from transit planning as well as multi-agent pathfinding, the vertices are the depots and the package locations that we have been given, as well as the transit stops of the transit network, which are time-stamped, if you remember. Or I guess it makes sense because they're following a timetable. I guess if you remember was wrong, I didn't mention that before. The edges in this graph are either represent the drone taking a transit option, so it just sits on a transit for some edge in that transit route, or flying to a connection. And these edges are either time constrained if the drone has to make a time connection, or they're time unconstrained if it's either not doing anything or it's flying from its last stop to the goal, because the goal doesn't have a time constraint, right? Or the goal as in the delivery location, or it's going back to the depot. So those edges are time unconstrained. Now this is key to our algorithm. For every drone's path, there are two separate functions that we need to care about, which could be completely separate. The first is the edge cost, which is the travel time, which is literally the elapsed time to do this, for the drone to go, to traverse that edge. The second is the edge constraint, which is the flight distance, which is just along that edge, how much distance has the drone flown, if it's a flight edge, if it's an edge that involves it moving. And that's something we also need to track because there's a global constraint on how much the drone can fly. And both of these functions are additive over the path, over the path. Now, in principle, these two functions are completely independent of each other. The travel time to traverse, I mean, you can imagine they're correlated, of course, if it's flight, but they could be completely independent depending on the scenario. And it turns out that adding a separate additive constraint to a shortest path search problem, which originally just had a cost, it takes the shortest path search problem to a whole new complexity class. And that is something that we're going to have to actively deal with in our approach. That makes even the second layer more challenging than the classical multi-agent pathfinding problem. So a summary of our approach to do this, we use a well-known framework called conflict-based search to solve this problem, this multi-agent pathfinding with transit networks over the graph model that I described. So conflict-based search is itself a two-level algorithm. I know the levels are starting to get annoying here. Very briefly, the higher level tries to resolve conflicts, like where certain conditions are violated, between paths of individual agents that were computed by some lower level path search routine. And it resolves them in some abstract best first search fashion. And ultimately it returns, it is guaranteed under certain conditions to return the optimal feasible multi-agent solution. By that I mean the lowest cost based on whatever our high level, our overall objective is. It can be make span, it could be something else. The lowest cost multi-agent path, multi-agent solution that is also free of conflicts. And conflicts in general could mean two agents being at the same vertex at the same time, or the same edge at the same, or traversing the same edge at the same time. I'll talk about what the conflicts are in our specific scenario in the next slide. In particular, in our framework, we use an enhanced version of conflict-based search that instead of using best first search like A*, uses bounded suboptimal focal search, which is like reaching back way into the classical planning community, because it's much more efficient in practice. And the state-of-the-art experimental studies on multi-agent pathfinding for large multi-robot settings, this is what Amazon's multi-robot warehouse stuff uses, for example, has borne out that enhanced conflict-based search, which uses focal search, is much more efficient in practice than the optimal version, which is conflict-based search. So that's nice. But remember, so conflict-based search runs an individual path search, right, for an individual drones, and then it looks at conflicts that have arisen between them and resolves them, rather than running the entire thing jointly, which would be fairly intractable for large numbers of agents, right? However, our individual drone, per drone path search, was over one, a large transit network, which we have to think about, and two, there was this constraint function. There was this flight range constraint, which is in principle decoupled from the cost. And for these settings, the typical conflict-based search formalism isn't suitable at all, because it doesn't make these assumptions. So what we had to do was develop a custom per drone path search algorithm, which is like its own thing in and of itself, that one represents the graph implicitly instead of explicitly enumerating all of the edges, which would be completely intractable for our network sizes. And two, finds bounded suboptimal paths that also satisfy this arbitrary constraint function that, again, the classical conflict-based search doesn't account for. And so that's a subroutine that wasn't in the literature, and we had to develop that and then build enhanced conflict-based search up on top of that. And putting all of that together gives us a bounded suboptimal multi-agent pathfinding algorithm that also respects the constraints of our drone delivery problem. Yeah, I know it was a bit to take in, but hopefully at least the interacting components make a little bit of sense. Now, I've been mentioning conflicts a little bit, so this next slide has only pictures. There are two kinds of conflicts that we have to consider in our specific problem. The first, we call it a boarding conflict. Well, I guess there's some text. It's when two drones try to board the same transit vehicle at the same time. Maybe this could be done in practice, but we want to be conservative, so that's a conflict we want to avoid. And we resolve that by forcing either of the drones to board at the next stop. And then which of those makes sense to do is something that the conflict-based search routine decides, which conflict resolution makes sense. The other is a so-called capacity conflict, because of course transit vehicles have a finite capacity and we don't want it to be exceeded. And in that case, to resolve it, we force some subset of the drones to leave so that the others can board, or the drone that considered boarding is just not going to. And again, which resolution makes sense is something that conflict-based search figures out. Okay, so I've gone over the high levels of the two parts of our framework. I'll make a couple of more quick points about the overall framework, like that sits on top of these two layers. The first point, as I alluded to, is that subsequent deliveries for a drone can be executed by computing the next path for the drone that finishes. So we don't have to do planning for a sequence of tasks, which is that much harder than planning for one task per agent, right? So we plan one task per agent for M agents. That's an M multi-agent pathfinding problem. And then if one of those drones finishes earlier, which will happen, we'll just replan for that drone. And we'll compare a couple of replanning strategies and our results. This is fairly obvious, so I won't elaborate this further. The second point is a bit more involved and is particularly relevant for this hierarchical framework. When I was discussing the allocation, if you recall, I asked you to assume that the travel time estimate for the drone from the depot to the package location was given to us. Now, of course, since this is a two-stage solution, the solution of the first stage constrains the solution of the second one, the quality of that estimate determines the delivery sequence chosen by task allocation, which in turn decides the starts and goals for the multi-agent pathfinding layer, right? The depots and packages. And that in turn determines the solution at the end of the problem, which is the overall mix span at the end of the pipeline. So the quality of that estimate constrains the multi-agent pathfinding layer, which constrains the resulting solution that impacts our real world objective. And so what we try to do here is we try to use a surrogate cost estimate that actually tries to account for travel times that using the transit network, but does not do the extremely expensive step of computing paths over the transit network while doing the allocation, which would no longer make this approach decoupled, two-staged, and would be intractable, and is something what a mixed integer linear program approach would try to do. It would try to solve the allocation while doing the multi-gen pathfinding jointly, and we expect that would be completely intractable. Now, to give you a little more intuition on the surrogate estimate, remember we had this allocation graph, right? Let's focus on this one edge. And we're trying to estimate the drone travel time from depot D3 to package P1. One surrogate, which might be what you thought initially, is just the direct flight time for the drone to get from that depot to that package. It's very cheap to compute. We can just do it obviously through physical computations, right? But it could be of really poor quality, especially if we expect the drones to need transit to get there, right? Because it's going to maybe consider out of range packages, or it's going to give a very optimistic time of direct flight, whereas you might have to wait for transit and so on. What we try to do is something a little more involved, but that we think is more representative. So given the area of operation, in this case, North San Francisco, we sample a bunch of representative points. We pre-process the time for a drone to get from these points to each other, all pairs, using a representative snapshot of the transit network. And we store this offline. These sites induce a Voronoi decomposition of the area of operation. So in runtime, given a pair of arbitrary locations, we look up the preprocessed time using the transit from their nearest neighbors. Of course, the quality of this depends on how many points we're sampling, and that in turn makes the surrogate more expensive to compute, but that is still a preprocessing step that we can do for a given area over a representative transit window. And we'll actually compare briefly the effect of these two surrogates on the eventual solution quality. Okay, so that brings me to the end of our framework. I'll now present a few of the results. There'll be a lot of numbers in the tables coming up. I was too lazy to kind of come up with custom subtables, but I'll highlight specific things that are worth noting and don't have to worry about the rest of the numbers. There are no fancy graphs, unfortunately, so bear with me. We'll evaluate the two components of our framework. We've already shown that the task allocation is near optimal, or I guess shown by Faith, it's in the paper. So what we really care about is real-time scalability in terms of absolute computation times with respect to the number of depots and packages. Yes, it's polynomial time, but what are the kinds of numbers we're getting in terms of computation time? For the multi-agent pathfinding layer, we'll evaluate both the scalability to the size of the transit network, you know, how much time is it taking on commodity hardware to compute solutions for these large networks? What's the make span, the real world make span of solutions we're getting for these deliveries? And we'll briefly investigate the surrogate cost function and the replanning strategies. As I said, baselines don't really make sense in either case because our problem formulation is quite specific in this way, and there's no exact previous work that solves it directly. And a mixed integer LP formulation wouldn't really be tractable given the number of variables and exponential constraints. Again, happy to talk about that offline. For specs, we use Julia and my desktop, which is 6-core, 16 gig RAM. Okay, now we have a few tables coming up. I'll talk you through them and then we're done. So for the task allocation computation times, I'm just showing a subpart of the table where along the columns, you have the number of packages increasing, and along the row, along a row, which I've blotted out the rest of it, you have the number of depots increasing. These times are in seconds, and just note generally how the runtime increases roughly quadratically with the number of packages as we go down the column, which kind of makes sense, matches with our intuition. It's a little between quadratic and cubic, so it's a little more than quadratic. Similarly, along a row for the same number of packages, as we increase the number of depots, again, it's roughly quadratic in the size. And then, you know, I have this full table in the paper. Don't have to worry about all the rest of the numbers. Just to point out the real world implications of it, take a scenario with 10 depots, the one I've highlighted, 10 depots and 5,000 packages. You know, that's a reasonable size, say over half a business day in a moderately sized city, right? And that's computing the allocation in about 1,000 seconds, about 17 minutes, right? Which for something that's then going to be executed over 7-8 hours or 6 hours, half a business day, seems reasonable. And again, remember, these are grad student numbers. I'm sure we use Julia's, we didn't even use Gurobi, we used GLPK. So If you probably had a distributed LP implementation for the connecting tours and some really hi-fi hardware, you could speed this up orders of magnitude. So the point is, even on commodity hardware, they're not completely intractable, which is nice given for 5,000 packages and 10 depots. I mean, nominally, the constraint matrix is 50,000 cross 50,000, right? So just—
Hey, Shushman?
Yeah.
Is the idea that you would run this like overnight kind of a thing, or like in the morning? Like you have, like, can you speak on what the rate is that you're gonna solve this?
Presumably, you know, let's say at the beginning of a business day, you get a set of deliveries, or you could have gotten it overnight from people who've made their deliveries the previous night. You get it at the beginning of the business day, you get all of the deliveries that need to be made that day, or at least that half day, right? And then a priori, if you know, okay, I need to make 5,000 deliveries in Menlo Park, Palo Alto, Mountain View over the 6 hours, the half business day, at the morning, you could compute these solutions and then execute that, right? If you have more coming in instantly, there's going to be some buffering. So maybe that goes into the next half business day horizon, right?
Cool.
Yeah.
Thank you.
Yeah, of course. For the multi-agent pathfinding layer, I talked about, we have these two scenarios, the North San Francisco and DC metro area, over which we actually compute the paths, or whose transit networks rather, that we use. And the North San Francisco area is about 150 square kilometers. The bus network, SFMTA, has about 4,200 stops. The DC metro area is about 400 square kilometers. The bus network has nearly 8,000 stops. And I parsed this data from the open source GTFS, which is what Google Maps uses. It's pretty cool, by the way. You should really check it out if you need transit stuff. Very well annotated. For time, I'm only going to discuss the North San Francisco results, but I'll show a simulation on DC as well. The drone model, as I said, very simplistic here. We assume a conservative flight range of 7 kilometers per trip, and an average speed of 25 kilometers. And for you Americans, I have the miles. So this next table is a lot. It's like, I can't even with this table, but I won't show you all the numbers just yet. This is kind of to say that we have tried to do an extensive analysis of various aspects of our framework. Before I show you any numbers, I mean, numbers are what they are, right? I think the metadata is more interesting here. What we're going to do is, for a given scenario in San Francisco, we're going to vary the number of depots and the number of agents, the number of drones over a city. The delivery locations were randomly generated in a bounding box. We ran the allocation algorithm on the number of packages, and then we took the first depot package return task for each of the drones, right? And we forget about the rest of it because we only care about one path per drone simultaneously. We took that set of paths, and then we ran our multi-agent pathfinding solver, the stuff that I talked about, on that set of paths. And then the numbers I'm going to show on the right columns, all the columns on the right, are statistics on those paths over 100 different trials for each setting. So if that general picture makes sense, I'll just show you the first row, and I'll talk through that, and then I'll highlight just the extremes of the remaining. So for a setting where we have 5 depots, randomly generated depot locations, we didn't try to optimize them, and 10 drones, we chose a large number of packages, many more than 10, ran the allocation such that we have at least one task for each of the 10 drones, and then we ran the MAPF solver on that. So over these 100 trials, the median computation time was, so yeah, it's 0.6 seconds. All these times are in seconds. The mean was 1.2. The variance is due to the fact that there's so much difference between mean and median is, especially in the computation time, is a feature of conflict-based search. The more high-level conflicts there are, the much more bulky it gets. And that's just, and these conflicts can arise depending on the distribution of packages. So that's why there's really a lot of variance, even with 100 trials. The range extension is just showing the effective distance drones travel, which is the geographic distance between their depot and their package. How much more is that than their range, the 7-kilometer flight range? So it's kind of telling you, oh, this is how much I can extend it. And there's obviously the mean, and then there's a maximum in that of that set. And I've shown both. The same is for transit. What's the average number of transit options that I'm using, and what's the maximum that any drone is using? And these are all showing that, yeah, there is a benefit. The drones are actually using the transit. And you'll see that in some settings, they won't use the transit when it doesn't make sense to do so. And then finally, the make span is the real world time in seconds to deliver these packages. So this is about 42 minutes. So if you had a set of 10 drones, the worst package of that set of 10 would be delivered in 40-something minutes, which is, it's nice. So I ran this for a bunch of depots and drones just to cover different aspects of coverage. We don't have to go through all of the numbers. I just want to highlight the extremes of the various columns. You can see even for 100 drones, we can compute these paths in about a few seconds, which is nice. The maximum range extension is 3.6, so that's the second oval from the left, which is, that's quite a bit of extension, 20-something kilometers, 30 kilometers. The average transit use on the most is 4.2, which is, okay, you're using transit 4 times per trip, which is pretty extensive. And then the worst make span for any of these scenarios is still under an hour, which is, again, this is all using the network that we have, but it's still nice to have some sense of the real world times to do this, right? And just one more thing, which isn't in the oval, but if you look at the case of many depots and many agents, which is the last row, you see it's not really using transit as much because a depot is close enough to its nearest. So 20, 50, for example. There are many depots, which is a little unrealistic, and relatively fewer drones. So relatively fewer deliveries considered one at a time. So the nearest delivery is likely to be much nearer the nearest depot. And in that case, it makes sense to just fly directly, because if it's within your flight range, why not? Why wait for transit, right? Why burden the public passengers traveling there? A few high-level takeaways from this transit analysis. I mentioned this before, but this is a feature of conflict-based search. Conflict resolution is a bottleneck. So, that's something that we observe. And for the Washington DC, there are higher plan times and make span across the board in general, because the network is larger, less well distributed. So the single agent search is slower, and there are more multi-agent conflicts. I didn't show the numbers, but I just wanted to show one video of the same simulation running in Washington. This is like one simulation picked. It's not necessarily the cherry picked one. So there's a lot more drones not using transit than they are using transit. I've also increased their range a little bit, because 7 kilometers is just too constrained to find paths over an area of 400 kilometers square. But anyway, the point is we run similar things on the drones. I'm running short on time, so I'll just overview the 2 other results that I promised to talk about, the replanning strategies. There's actually not a lot to say here, which is just that there are 2 replanning strategies. One where when one drone finishes, we just replan for that drone, and we don't touch the other drones that are continuing to execute. And the other is replan M, which is when one drone finishes, we replan for all of the drones, where the other drones, we interrupt them and we replan for them as well. And basically what this all shows is that replanning for just the drone that's finished is perfectly fine. We compared on a subset of scenarios, and you can see the solution quality is mostly similar, and the time for replanning for one drone is much faster, which is of course what we expect. The point here is replanning just for the drone that's finished is sufficient. We don't have to worry about replanning for all of the other drones. So this can be a truly receding horizon approach for executing a sequence of deliveries, which is nice. We can do a lot more asynchronously. Let's not worry about the numbers. And then lastly, I compare the 2 surrogate estimates, and this time I'll show the numbers on DC, since I showed something in SF before. I've just copied over the planned time and make span for pre-processed, and the numbers I showed before were using the pre-processed surrogate. So the task allocation layer was using that pre-processed surrogate to compute solutions that were then given to the multi-agent pathfinding layer. In this case, I contrasted it where the allocations are obtained by using this direct flight surrogate, which is cheap, right? And I compare the computation time and the solution quality, plan time and make span for all of these settings. I'll just highlight one of these cases. You can see that the preprocessed is both faster than the direct and better. So it's both more efficient and it achieves a better make span. This isn't always the case, but the point is, the only takeaway from this is the surrogate kind of matters. You can't just abstract it away as this naive thing that you can think about later. It matters in this 2-stage approach, and it matters in the real world cost you get at the end. And if you're in a scenario where drones are likely to use transit, you should use a better surrogate. And it's really suitable to maintain both surrogates and switch between them depending on scenarios. If you're in a scenario where you don't expect drones to use transit, you should use the direct flight surrogate. And the numbers show that as well. That's like the 4th main takeaway. Okay, yeah, we're at the end, thankfully. So in summation, I discussed this 2-layer framework for solving large-scale drone delivery over transit networks. We have a near optimal polynomial time task layer on top of a bounded suboptimal multi-agent pathfinding layer. A couple of future direction steps, doing case studies for the operational cost, externalities, and maybe some algorithmic extensions, incorporating uncertainty, which my single agent work did do to a certain extent. And you could build, since they all use similar frameworks and representations, you could build this on top of that, where the final last mile of executing the paths, instead of assuming the simplistic dynamics model, could assume a stochastic kind of more drone-based dynamics model, multi-rotor or whatever, and be incorporated in that framework. You could think of doing delivery time windows. Some work I've done with Dorsa and Jeanette is trying to do allocation with time windows. You could route vehicles and drones jointly, and you could even place the depots optimally for coverage. Okay, I'll leave the contribution slide here. And if there are any last questions, happy to take them. So yeah, thanks for your attention.
Okay, thank you, Shushman. I guess we can do the upload on Zoom.
Oh yeah. You're welcome. Yeah, thank you. Yeah, I know some people probably have to run, so feel free to. It took a bit longer than I planned because I've added more content, but yeah, I'll stick around for a while.
Yeah, if there are questions to Shushman, I think we can take them now, or you can ask your questions offline too.
Okay, could I ask a question?
Yeah, go ahead.
Sure. So I'm kind of curious, Shushman, I guess a little bit of a broader question for your hot takes on how close we are to deploying these types of algorithms that you presented. And I guess one aspect I'm curious about is when you were showing that San Francisco and Washington, are you using real public transportation routes? Like, are the public transport routes we have today in our city infrastructure sufficient to handle these sorts of load, or do we have to build more infrastructure? Or do you have to use private fleets like Uber and Lyft or these sorts of things? Can you comment on this?
Yeah, I mean, the caveats are, of course, ours was we did very little on the operational side. So we randomly generated locations. You'd probably have deliveries proportional to zip code and income and things like that. And that might strain systems more. Also, bus networks maybe they operate more in lower, or they're used more by people in lower income areas who don't have their own transit. So there's a non-uniform distribution of load, and that might also be something that needs to be accounted for. I think in terms of, well, there's a physical infrastructure, which of course, you'll have to think of docks on these vehicles, be it cars or buses, which is of course a mechanical and design problem. On the algorithmic infrastructure, it's possible. I mean, these are very preliminary results. That's why I said really, especially for the transportation community, to run more case studies. And I think some of the collaborators on the grant are looking at those aspects of it, to run case studies, incorporate actual costs. Like these costs were just simple delivery time. There are resource costs, there are economic costs and all of that, and really look at a proper actual cost benefit analysis. But on the algorithmic side, I think it's possible. I mean, these are definitely initial promising results that say, okay, you set up the networks we use were the SFMTA bus routes with the actual timetables that they had over the actual stops that they had. So that's what we parsed from GTFS, similarly from DC. So those are quote unquote real in that sense, that they're using real transit data. Right. And the locations, while randomly generated, except for the ones that are outside the city on the water, are, they're still geographic locations. Most of them are street addresses. So it's about as real as it can be right now in that sense. I think 2 or 3 biggest things that would have to happen for this to potentially be deployed is, the logistics cost of coordinating with transit and personal vehicles, and running separate sites to see if it makes sense to use Ubers or personal vehicles in places where public transit is insufficient, which might be in, say, Los Angeles, for example, right? With Ubers and stuff, you get a lot more, as before, you get many more feasible solutions, you get a larger problem space, but you also get a much bigger computational challenge because the scale is potentially much larger, and you have many more routes being generated. So, and that trade-off now needs to be managed.
Yeah, gotcha, thank you. I ask because it seems like you've got the algorithmic side pretty much in a good spot. And so you kind of start wondering yeah, you kind of want to apply it. Very cool.
Yeah, thanks. Yeah, we'll see. Exciting. Cool.
Is there any other questions? Okay, if not,
All
I'm
right.
going to stop recording. Thank you again, Shushman, and see you all later.
Thanks everyone for attention. Yeah. Take care, everyone.
Yeah, thank you, Shushman.
Take care. Bye-bye.